Okay, hello everyone, welcome all. I'm sorry for a little delay there. We were just trying to work out a few issues in checking into the Zoom. So without any further ado, we will go ahead and start our webinar. So thank you to everyone for joining us today. We're very pleased to continue our work and collaboration on nanomaterials with the BRS Secretariat. As many of you know, UNITAR was a co-lead of nanotechnologies and manufactured nanomaterials with the OECD under the old SICOM framework. And we now have an opportunity to continue our work under the global framework on chemicals and the Basel Convention, as well as other international agreements, whether they be current or in the future. And we'll hear a little bit more about that later in our webinar as well. As you may know, UNITAR has worked with many countries in their nanomaterial strategies, and as well as nanomaterials, we've helped share WHO's guidelines on workplace safety for nanomaterials and helped coordinate international, regional, national activities on nanomaterials. We have proceeded with a webinar series, particularly with the BRS Secretariat, trying to link to plastics. And this is the third webinar we have in our series on micro and nanoplastics, each time intending to go a little bit deeper and focus on different topics where we've had feedback on specific areas of interest. We had our first in October 2024, our second in March 2025, and here we are today with our third. So without any further ado, to move on ahead, we will introduce our first speaker. So we have Mr. Thomas Bucheli from the Federal Department of Economic Affairs, Education and Research, and he will give us an overview over current activities related to microplastics in the agro-environment. So Thomas, thank you very much for joining us. Please go ahead and introduce yourself, and then I will let you share your screen and present away. Thank you.
Thanks a lot, Olivier. That's a pleasure to be here with all of you. So I try to share the screen in the presentation mode, which you now should see.
Yep, that's perfect. Thank you.
Perfect. Thanks. So I was asked by Georg to present a little overview of our activities, both as Agroscope, so the Swiss Federal Office for Institution for Agronomic Research, and specifically on a project that is a joint venture of some institutions in Switzerland. In that way, I will cover in the second part. So these are my main co-authors here, essentially from that consortium, Agroscope, EAWAG, ETH, and we even have a few people online as I speak. Yes, so what is Agroscope doing? We are having a bunch of activities that all started off with some mass flow analysis based on earlier work by Bernd, who was an early presenter of that webinar series, as I understand. We had an early on quite fruitful collaboration with Michi Sander from ETH on biodegradable mulching foils. We do, as I mentioned already, collaborate with EAWAG and IMPA, two institutions close by from the ETH domain. We jointly run an analytical laboratory for microplastic analysis, and then showing some first data from that consortium here. We have further activities within Agroscope that deal with soil structure, microplastic influence on soil physical parameters. We also are involved somehow with other colleagues that are mentioned here on effect related projects, in this case exposure and uptake of microplastic by soil arthropods. And we also think about remediation and getting rid of plastic residues that might enter agricultural soils, as you will see later on during the talk. For reasons of brevity, I have to focus a bit on some of the issues, and I'll cover now the first three aspects that are highlighted here. First of all, plastics in agriculture, they have a lot of advantages. They are widely used for good reasons. Here is a list of qualitative benefits that plastic use in agriculture can have. It is used as a crop protector. It can extend the cultivation period under which you can actually grow a crop. You have improved water efficiency aspects, less fertilizer pesticide applications, less runoff, for instance, also potentially prevention of soil erosion. It is often a substitute for alternatives that are equally well suitable maybe, but come with other disadvantages such as price or other effects that you don't really that you don't want, such as those scary shots, for instance, to deter the birds. Overall, plastics in agriculture lead to higher crop yield. We generally distinguish between different kind of input sources to agricultural soils when it comes to plastic. So obviously there is a primary input from applications that are meant to be used in a proper way. I have a few examples here. Maybe the most prominent and widely used one is silage foils for grass and fodder production and storage. They come with an added value, of course, and if you use those materials properly, so you recycle them properly, the actual residual fraction in agriculture ecosystems is low. Then we have other applications, such as those mulching foils that you see here as examples. They have an added value, as mentioned before. Their initial application amount may be locally high. Again, depending on whether we talk about persistent or biodegradable mulching foils, the residual fraction is at least initially high, but might degrade. The problem that we have in practice is often that also the general public cannot differentiate between biodegradable and persistent mulching foils. And often you see pictures like that on agriculture fields where people are a bit uncertain what kind of plastic foils were actually used. So either you use persistent one, then you have to remove them. If you use biodegradable ones, then you actually should plow them into the soil for better dissipation afterwards. These pictures here can create quite a bad image in the public with respect to farming practices, and should be avoided. Overall, as I made the point, plastic in agriculture is beneficial. That's why it is used widely, and it is actually a whole industry. Here is an example of some branch-specific journals that actually appear regularly. Also, you can actually download them on the website indicated here. Now, secondary inputs are, of course, also possible, and they are not of any beneficial value. They are not intended, and they originate predominantly from littering or from residues of various forms of biowaste, such as digestate and compost, that are applied as either fertilizer or soil improvers. They are unwanted, and they are negatively perceived again by the public also. And of course, by definition, the residual fraction of such materials will be 100% because we don't want any of that in our soils. Now, you may have seen, if you follow the webinar regularly, a graph such as this one here from a paper by Kawicki and Novak. Bernd Novak was certainly presenting that. He did a mass flow analysis of the major polymers in whole Switzerland, and essentially covering 7 different polymers here. Here we have polypropylene as an example. Now the focus today is on that tiny little spot here on agriculture. And for that we teamed up with Delphine Kawecki a couple of years ago and expanded that module here for plastics in agriculture. So we have zoomed in on plastics in agriculture now. And this is the picture here. You essentially have different uses here, different materials with amounts in Switzerland of 50 to 6,000 tons per year and application. The detailed numbers are presented in a paper that is referenced in the next slide, I think. And then here different agricultural crops. And obviously the system is quite complex. We have inputs to soil, residual inputs, so remaining fractions of what is originally applied of that amount over here in the order of 1 to about 60 tons per hectare and year. These are as expert estimates by the researchers. If we zoom in on individual applications, you see first of all different types of plastics used for different purposes here, the total amount that is used, the input rate that we estimate that remain on the soil after use. That is essentially the product of these two numbers here. So what is remaining in the soil per application type, and then also normalized to the actual area of a given soil, of a given crop culture where those products are used. So really grams per hectare and year where they are specifically used. Now altogether again, these are about 16,000 tons per year, and we estimate that in total we have about 160 tons per year are remaining on the fields. Now a couple of individual examples. We can differentiate different situations. The first one here, we have large amounts of those silage foils, but the input rate is rather low because you can easily recover those silage foils after use on the farm level. So the absolute input is rather low, and per area it is even less relevant. So that application probably doesn't cause major exposure to plastics. A second case are those polyethylene, so the persistent mulching foils. We have an average amount used here of about 300 tons a year. The input rate is higher and above here, but probably average in total. The absolute input is also not really considerable, but if you really consider that these amounts are only used on a certain range of agricultural use, particularly vegetable production or fruits, special cultures, the actual input per hectare is considerable. The third case here is the unwanted use. So this is littering. Overall, we estimate a rather low absolute number, and since this is unwanted and makes it to the soil, by definition, we have 100% input rate. So the whole 80 tons are going to agricultural soils. But again, since this happens to a large area, essentially whole agriculturally used land, that hectare-based fraction is actually rather low. And the fourth case would then be the alien materials, plastics in compost and digestate. Similarly, a relatively small number in absolute terms, again, 100% remains on soil. And if you then consider only the areas that actually receive compost and digestate, that input is actually considerable. So it really depends on not only how much, but also on what area and what's the remaining fraction after use. Based on these numbers, we tried to come up with the first risk assessment, and we kind of came up with a worst case scenario on a hypothetical area. So we assumed that on a given agricultural area, this one was since the 1950s, so when plastics started off really to be used commonly, increasingly, exponentially, So let's assume we have over the last 70 years or so littering to a hypothetical area. Then we assume we did fertilization by sewage sludge application over the same period roughly. I mean, it's forbidden since 2005 in Switzerland, but also maybe 50 years of sewage sludge application with the microplastics that come along with it. So about 260 kilos we estimated per hectare. And then a replacement of that fertilizer by another kind of soil amendment material that is compost and digestate, another 125 kilograms per hectare, plus mulching foil applications. So really a worst case, assuming this has been a vegetable cultivating site. And if you sum up all those numbers, you end up with something like 500 kilograms per hectare over that period. Now, if you do some assumptions, calculate some predicted environmental concentrations on a gram or percent per kilogram soil basis, you end up with something like 0.02% of plastics in soil. That is considerably lower, still a factor of 50 to 100 lower than the total organic carbon content that we have in soils in Switzerland, simply for comparison. The number is maybe a bit far-fetched, you might say, but if you compare it with some literature data in heavily used agricultural areas in China, we are in the same order of magnitude. Okay, so that was the predicted environmental concentration. Now we tried also to come up with a predicted no effect concentration. At that time, 2019, this is the paper I was referring to, we could find at that time roughly 10 papers that reported field studies or lab studies of plastics exposure to certain soil organisms. And here, that's the important part of the graph. You have the concentrations on a weight per weight basis from low to high. And the individual papers showed then effect concentrations, those response curves, for instance, up here in the order of 50% almost of the soil and down to something like 0.1%. So that defines our predicted no effect concentrations as being 0.05% based on those studies. And here again, for comparison, our PEC level, which is lower than that. And as a consequence, we come up with a risk quotient, that is the ratio of the PEC to the PNEC of about 0.4, which means lower than 1, which means currently no risk based on that assessment at that time. But you have to consider that it is really based on worst case in terms of PEC. It is not analytically confirmed yet. That's what we all try to do now, develop the corresponding analytical methods. And also on the PNEC side, it's mainly lab studies, not really real agricultural systems. The plastics were not really generalized or standardized in any way. Everyone did kind of a same setup. So it is really preliminary, I would say, this risk assessment, and it should be periodically renewed. That brings me to the second part of the talk, how biodegradable are biodegradable mulching foils. As I indicated before, they are increasingly used as substitutes of polyethylene, so the persistent foils. And they consist mainly of two biodegradable polymers. This is the polybutylene adipate coterephthalate, PBAT, and the polylactic acid. So a composition of those two polymers that constitute the biodegradable mulching foils. So we used some of those commercially available products for incubation studies at different scales. And obviously we needed some positive controls, that PHBH compound here, known to be biodegradable, and again, polyethylene as a negative control at the various scales. And we used those materials to conduct, I would say, a unique exposure or incubation study at different scales. Now, why are we doing that? There is a European standard that commercial vendors and producers of such foils, biodegradable foils, can use to to prove that their specific product is biodegradable. So you would have to incubate your mulching foil at a given laboratory condition, and within 2 years, 90% of the carbon must be converted to carbon dioxide, either on absolute terms or relative to, again, a positive control such as cellulose or the positive control that we use here. Now the question is, this is laboratory, what happens in the real field? For that, we used 3 fields in our agricultural research station Reckenholz, from which I'm talking to you today. 3 different soils in the close vicinity, a few hundred meters apart. 2 are really under agricultural use. One is an ecological compensation area. And without going into further detail, the major difference is here the pH, the rather acidic pH of soil number 1, yes, of 5. Right. So what we did then for each of those soils, we used 2 commercial foils from those producers here, positive and negative controls. We used 5 different time points over a period of up to 3 years, and we used 4 replicates for every incubation combination. That resulted in something like 650 samples, and they were then quantified based on that methodology here. It's a quantitative analytical method that allows to quantify the residual material after a given incubation period based on quantitative NMR. And we used laboratory conditions, greenhouse conditions, and real field situations. Now, what we see here in the laboratory incubations, the good news is, yes, the positive controls stay degraded over a period of 3 years to by more than 90%. That's fine. That's what we needed, what we expected. Polyethylene, the negative control, didn't degrade at all, also to be expected. And here, the PBAT and PLA with some partial comparable degradation per soil, but really strong differences between individual soils. This is the most acidic soil that I mentioned before, soil number 1. So even in the lab, not much of a degradation there. Now, if you go to the field, we see again limited degradation of the 2 polymers, the biodegradable polymers. There is some difference here again, or in this case, between the copolymers. Again, soil number 1 shows almost no degradation at all. But what is most strikingly here, most importantly, even the positive control wouldn't fully degrade over 3 years. That's considerable. That may be surprising, and it makes it really relevant in terms of that guidance document I showed before. 90% on absolute terms or relative to that positive controls. That's what the biodegradable mulching foils need to be capable of doing. So this puts that ordinance or that legal document into some kind of a perspective, and shows how future evaluations of such commercial products should be done. I move on to the work that we do together with colleagues, as indicated in the Swiss Consortium on Microplastics Fate and Behavior Analysis in Air, Water and Soil. It is a consortium consisting of, apart from Agroscope, with EAWAG, Dr. Ralf Kegi is here, the main supervisor, and EMPA, Dr. Christoph Hügelin, both located in Dübendorf. We share, each of us, a PhD project, and try to really align our activities mainly along the analytical chain. The whole project is funded by the Swiss Federal Institute for the Environment, or Office for Environment, sorry. Okay, and I give now 2, this is still work in progress, I give 2 case studies to give you a flavor of what we are up to. The first one is on the monitoring of atmospheric deposition, that is dry and wet deposition of microplastics in Switzerland. For that, we use the National Air Monitoring Network, NABEL, operated by Christoph Hüglin and his group. And we have selected 5 locations, one in the south of Switzerland, 2 in the western part, and 2 in Zurich in an urban and semi-urban context. Chaumont here is relatively remote in the Jura and the Swiss Jura. And we do sampling of active and dry and wet deposition over a period of 4 weeks, altogether over a period of a year. So this is in all brevity the analytical chain that we do. We use rigorous quality assurance, quality control measures in as much as we use a surrogate standard here that are added at the beginning of the exposure, the sampling campaign, and then at the end of the 4 weeks period, again with a differently labeled polymer. Then we go over some cascade filtration to capture the size range of 200 to 15 microns. And then we need different oxidative cleanups to remove residual organic matter. We often also do density separation to get rid of other particles, soil-borne particles, and also biotic particles in combination here. Then we first do an optical microscopy step with an optical light microscope. And here you actually can see the surrogate standards again, the red and the blue polymers that give us good confidence on the recovery of the method over the whole analytical chain. And then we move on to a focal plane array micro FTIR, where we can do on a pixel by pixel level FTIR spectra and do the chemical conformation and identification of individual particles. The whole thing is very laborious. It takes about 17 hours net data acquisition time with that instrument alone. What we do in the consortium is that the whole sample preparation is matrix dependent, but we really combine the approaches, particularly on the analytical part, and subject all our samples with a coordinated way in a very similar and comparable way, also to be able to compare our data across different matrices eventually. Now, this is some first data from Narayan Ashta's thesis here, showing at one time point data from Chaumont, so that's the remote area, and here data from Zurich. And you see, first of all, quite a zoo of polymer particles, very diverse, not really any domination by a few polymers you might actually expect. And you see also differences in terms of dry and wet deposition, particularly in that urban location of Zurich. Please note also that we face difficulties in terms of limits of detection that has to do with the absolute low numbers of particles. These are number concentrations here. So we're talking about 100 to 300 particles here on a filter after 4 weeks. So really we fight against the low concentrations, if you want, or with the low concentrations. Now you can obviously calculate from the raw data then fluxes or mass flows either on a number-based concentration, or by some further assumptions you can also derive mass-based concentrations. In the numbers we are in the order of a few hundred particles per square meter and day. The masses account for approximately 20 to 50 micrograms per square meter and day.
Thomas,
yes,
just to jump in, I know you're coming towards the end, but just if you could move through the last few slides fairly quickly, that would be very helpful.
Good.
Thank you.
Good. Okay, so here this is about 0.05% of the total atmospheric deposition. So again, a very marginal fraction. And if we do an upscaling here, extrapolating to the area of whole Switzerland from the one filter. Obviously, that is an assumption. We add up with something like 400 tons per year over whole Switzerland. Now, that can be compared with literature values, again, mass flow analysis by Bernd Nowak. And here he is in the order of some 100 tons per year. That's comparable for now, I would say. I skipped the second application. It would have been on wastewater treatment plants. Similar approaches here, similar data, mass balance is also preliminarily done, and we come up here with some 5 tons per year of microplastics that are entering the rivers or exported by wastewater treatment plants. And again, that number here compares surprisingly, but probably by accident or incidentally, with model-based numbers from Bernd Nowak in the order of, again, 5 tons. Yes, and that brings me to the conclusion. So we have microplastics. They are ubiquitously present in the environment. We knew that before. We now also knew increasingly that this is the case in agriculture with some specific input sources. Analytical methods are very, very challenging. I try to make that point. Quality assurance and control is essential, but often neglected. That's the good news here. We start now, for the last decade, we have only been capable of doing model-based number predictions, concentration predictions by groups such as Bernd Nowak. We are increasingly capable of confirming those data with actually measured numbers, and this is what the last 2 applications tried to illustrate to you. Risk assessment-wise, we are still not as far as I would say, particularly in the ecotox part. So the effect part is certainly a lot of work to be done. And really to conclude, the benefit of collaborating between institutions. No single institution can maintain such equipment, such a laboratory. It doesn't make sense to repeat the wheel for each and every institution. We should collaborate in a better way. And this is an example that I think is very successful in that respect. And with that, I apologize for maybe having been a bit long here, but I'm done now and give back to Oliver for the next presentation. Thanks.
Perfect. Thank you very much, Thomas, and no need to apologize. We have a little bit of flexibility. We also have a question and answer session at the end for anyone who would like to ask Thomas and indeed our other presenters any questions. You've summarized very nicely, so I won't try to do any of that for you, but I very much appreciate you sharing that. And we note the preliminary results as well, so that's great that we get an opportunity to at least hear some of that, and great that you also referenced one of our previous speakers linking to a previous webinar we've done. So with that, on the agro-environment, we will now hear a little bit more about the impact of micro and nanoplastics on human respiratory and immunological systems. Here we have Barbara Melgert, Professor of Respiratory Immunology. So Barbara, welcome. Please go ahead and introduce yourself and share your screen. Please let me know if you're having any issues with sharing. Barbara, please go ahead.
Thank you, Olivier. And thank you for inviting me. Quite daunting to be speaking to a body of the United Nations. I will share my screen. Well, introduce myself. I'm Barbara Melgert. I'm a respiratory immunologist from the University of Groningen. I'm interested in respiratory diseases and how they begin. And part of that, of course, is due to exposure to pollutants in the air. And in that respect, I got interested in microplastics. And I'm part of a big consortium in the Netherlands called Momentum, which studies the health effects of micro and nanoplastics. And my part of that is specifically the lung and also the immune system in the lung. So I will be talking you through effects of microplastics on the lung, on the immune system in the lung, and some of our results. So microplastics can enter the body through the lungs, through inhalation, through the gut, through ingestion, and through the skin, although this is considered a minor route because the barrier of the skin is quite more tight than the ones in the lungs and in the gut. So data from our Momentum Consortium actually showed that doing the modeling, that 80% of human intake of microplastics actually from inhalation, which makes the lungs a very important entry point of micro and nanoplastics. So in our task in this consortium was to determine what the risks are of microplastics inhalation. And then when we're talking about risk, there are three components to risk. There's hazards, how toxic are microplastics. There's exposure, how much are we actually exposed to? And of course, there's vulnerability, who is most sensitive. So I'll go through these three components while taking you through the data that exists. So how much are we actually exposed to? It's very nice to see the data from the airborne microplastics in Switzerland. So I've aggregated a lot of studies and there's lots of variability, but generally outdoor 1 to 20 particles per cubic meter are found. But the key message here in this slide is that the indoor levels are much higher, up to 500 particles per cubic meter. And most of these particles indoor are from textiles like polyester and nylon, the textiles that we use in our homes, the carpets, the clothes, etc. Outdoor particles can be very variable, but for the Netherlands, actually, it was shown that most of the particles are actually from tires, so tire abrasion particles. So based on all these data, modeling studies have been done, and also here it was shown that generally indoor exposure is much higher than outdoor exposure, but also that when we're talking about susceptibility, that the smaller you are, so the younger you are, the higher your exposure due to increased ventilation rates and being closer to the source of the microplastics. So levels for infants are much higher than for adults. So we did a study in the Netherlands to see what people knew about microplastics in the air. And we were interested to see if people realized that the indoor exposure is much higher than the outdoor exposure. And to our surprise, people think that the indoor microplastics are actually coming from outdoor. So that would prevent people from opening windows if they think that microplastics come from outside. While actually the levels outside are lower than indoors. So opening a window would actually mean that you could lower your exposure. So that was an important finding for us in our communication to the public. So there are particles in the air, but does that actually mean that they can enter the lung? And that very much depends on size. So for reference, I put a human hair here, which is 50 to 70 microns. And of course, the well-known air pollution particles, PM2.5 and PM10. So if we look at the lungs consist of conducting airways that transport the air into the more distal parts of the lung where gas exchange takes place. So these airways are tubes moving all the way down to the air sacs that sort of look like little bunches of grapes. So particles that are bigger than 100 micrometers don't really enter the lungs, they get stuck in the nose. And the smaller they are, the deeper they come. So for me as a pharmaceutical researcher, the ideal size to get stuff into the lungs is around 2.5 micrometers. If we then go even lower to the nanoparticles, then these can also be exhaled again because they stay suspended in the air. So it doesn't really necessarily mean that the smaller, the deeper in the lungs. It also means that the smaller, the higher the chance of being able to exhale things again. There are small particles in the air. Can we actually breathe them in? Are they found in the lungs? And the answer is yes. So there are not an awful lot of studies looking or having reported results about that, but the studies that have looked into this have found particles and fibers in lung tissue, and the most common ones.
Oh, okay. I think we missed the start of you introducing this slide.
Are you talking to me?
Yes, Barbara. Yeah.
Which slide exactly?
Just the one with this exposure. Microplastics are found in lung tissue. I think you might have cut out.
Oh, okay. I wasn't. Okay, so we know that there are microplastics in the air. We know that they're small enough to be able to get into the lungs. So are they actually in the lungs? And these are studies showing that they actually are found in lung tissue. So small pieces of plastic and fibers have been found in lung tissue. And the most common one reported across these studies are polyester, polyamide or nylon, and polyurethane. And the sizes differ between the studies, but are within the range of being inhalable. So we know that there's exposure. We know that there is exposure to the internal exposure to the lungs. What are the hazards of microplastics? How toxic are they? So when we're talking about inhalable microplastics, then there are actually three characteristics that could cause toxicity. One is particle related. One is additive related, so the chemicals added to plastics, and the other is absorbent related, so things from the environment that are absorbed onto the particles and sort of hitchhike along with the particles while they're being inhaled. So that is direct toxicity to the lungs. Of course, when the particles are small enough and can cross an epithelial barrier, they can also go to the blood and move to other organs. But for the sake of this presentation, I'm not talking about that. I'm just focusing on the lungs and its immune system. So what do we know about particle toxicity? Actually, we do know a lot about particle toxicity because a lot of studies have been looking into different types of particles that we can inhale. For instance, asbestos, soot, silica dust, wood dust, hay dust, cotton dust, lots of dust that we encounter in our working and living environment. And when we know what the drivers of the toxicity are, of course, as always, dose, but also the size, the shape, and the surface are important for determining the toxicity. So depending on how what the microplastics look like, they could have more or less toxic effects. So that is dependent very much on the type of plastic and the type of shape. So generally speaking, particles are taken up by immune cells in the lung. And if they're not able to degrade these particles, they will become inflammatory, and this will induce an inflammatory reaction in the lung. And when the dose is too high, this will be a general inflammation within the lung, leading to a higher chance of developing diseases like chronic obstructive pulmonary disease or lung fibrosis. So another aspect of plastic is that it contains additives that can be toxic as well. So plastics are, of course, monomers made into polymers. And during this polymerization, chemical additives and processing aids are added that can leach out of the polymer when it's being used. But also non-intentionally added chemicals can end up into the plastic material and can leach out, and these can cause toxicity. So a big study by Monclus, just published in Nature, found, combining all the data available, that there have been more than 16,000 chemicals reported for plastic, and a quarter of those were chemicals of concern, and an even bigger part of that we don't actually know. There's no data on toxicity data on these chemicals. And most of them are also not regulated. So there's a lot of potential for toxicity there. And then the third part is microplastics as pollutant carriers. This is sort of hypothetical. There's not a lot of health data out there to show that this is something of concern. So what do we know about inhalation of microplastics and lung effects? Well, most of our data there is actually from occupational exposure. So people working in industries that produce plastic or use plastic, like for instance, people working in the polyphenol chloride industry, studies have shown that they have an increased risk of developing asthma. They inhale a lot of the dust associated with PVC, and they can end up with dust lungs or scarred lungs, and they also have an increased risk of developing lung cancer. And the same for people working in polyamide industries, for instance, nylon flocking industry. Also, these people have a high chance of developing inflammation in their lungs, scarred lungs, and also an increased risk of lung cancer. And an interesting new category is people working with artificial stone. This is being used a lot these days to make kitchen counters. And the people who work with these kitchen counters have to sort of, well, saw into it, get exposed to the dust. And these people have a very high chance of developing lung fibrosis at a very early age. Lung fibrosis is a disease that develops normally when people are in their 60s or 70s, and these are people in their 30s already developing lung fibrosis due to the exposure to this artificial stone. So that was the data out there when we started our research. Most exposure is from being indoor, and indoor mostly has textile microplastics. So we wondered what textile microplastics actually do to our lungs. And to investigate this, we decided to first focus on the cells that are first exposed to microplastics. So here again, the lungs with the transporting tubes and the gas exchanging air sacs. And both structures are covered with epithelial cells that form the barrier between the tissue and the air. And on that barrier are immune cells that help with clearance of inhaled particles or bacteria or viruses. So we studied both these cell types, both the epithelial cells and the immune cells. So first, the immune cells, what we did, we isolated them from either human or murine lungs, and then put them in a plastic culture dish and added microplastics fibers from textiles. And our question was very simple. Do these cells see these plastic fibers? Because they're in a completely plastic environment. Why would they suddenly start doing something to these plastic fibers? And this is a movie showing you what the immune cells do. Do they ignore them? Do they attack them? So these little green blobs here are the immune cells, and the big rods stained in red were nylon fibers. And if I now start the movie, you will see that the cells really start looking for these fibers and start interacting with them. So they do not ignore these plastic fibers. They really try to eat them, which is very obvious in this photograph of a culture of immune cells. So the little round circles here are all the immune cells. And you see that here is one that has eaten 3 fibers. And of course, to be able to do this, it needs to grow. And usually this sign of being big and angry, it starts to become very inflammatory, starts producing mediators that induce inflammation in the lung. So moving on to the epithelial cells, here we have a slightly different model. We can also isolate, again, these cells from murine and human lungs, but we have to culture in a slightly different way. We culture them in a gel-like material, and it takes about 14 days, and then these cells start to develop into either mini airways or mini air sacs. So they really start to assemble structures that you also find in lung tissue. So while these structures were developing, we added the textile fibers to see what would happen to the development of these structures. So this is what it looks like in real life. Under a microscope, these bigger bubbles are the airways, so the tubes. But you also see these sort of grape-like structures, which are the developing air sacs. So because these both are in our cultures, we can see what happens to both when we add the textile fibers. So we use polyester and nylon as the most used fabrics that are found indoor. And here are results from quantification. So here we find the mini airways, and here we quantified the mini air sacs. So in control conditions, we find around 75 of these mini airways in a culture. And when we've incubated these cultures with nylon fibers, then there is a dramatic loss of airways, which didn't really happen with polyester. And we didn't see that big of a difference in the air sacs. So specifically, the airways were very vulnerable to nylon for some reason. And then, of course, our first question was, is this actually the fiber or is this a leaching chemical? So to be able to determine this, we had a slightly different setup. We had our normal setup with the fibers within the cells, so there was contact possible between the fibers and the cells. But we also added the nylon on top of this gel, so there was no direct contact possible. And to be absolutely sure that there were no fibers, we also washed the fibers, and we used the washing liquid to treat the cultures with. And the results were very obvious. So here again is the control condition with nothing being present. Here is our usual condition with the nylon being within the cells. But also the nylon on top of the cells and the nylon wash had the exact same result. It was a dramatic loss of airways, which tells us that it's not actually the fibers, but it's something leaching from nylon that is very detrimental to the development of airways. So we are still hunting for the chemical. I know there's 16,000 chemicals associated with plastic. We found in our fiber wash a lot of unknown chemicals, and we still haven't been able to pinpoint the exact chemical that is responsible for this effect, but we are getting closer. But that is a topic for another session, I think. So a little bit more information about who is most sensitive, who's most vulnerable. I already mentioned that children have a relatively higher exposure to microplastics indoors. Our mini lungs are actually models of repairing lungs or of developing or growing lungs. So if our model represents children developing their lungs, it would seem that being exposed to a lot of nylon would make them most vulnerable, especially if they're also being exposed to more nylon when being indoors. So we actually think that patients with lung disease that depend on repair of their lungs to be more susceptible to this particular effect of nylon, and children and fetuses. So what we now know is that microplastics are a novel type of air pollution, that nylon fibers are taken up by immune cells and they do not like that. They become inflammatory. That nylon inhibits the development of these mini airways, and that it's a leaching chemical responsible for this effect. And we actually know the exact biological mechanism behind the loss of the airways. I didn't show you that for sake of time, but we know exactly what is going wrong in the cells, and we can actually also treat it. So we can get the airways back with a specific treatment, but we don't know which chemical is responsible for this effect. So the key questions that we still need to answer is, does this actually happen in lungs of humans? Because, I mean, this was a model and not a real human. And what is the dose needed to see these effects? We know this for the in vitro system, but not for real life. So how many microplastics do we actually get into our lungs per day? Because the number of studies to estimate this is still a little bit too few to be able to estimate this very precisely. And of course, it remains really important to know which chemicals leach out of plastics. And we've looked at 2 types of plastics, but there are hundreds of types of plastics. What do these do? We don't know. So the implications of our result, we think most at risk will be children and people with lung disease. These results also make me very wary of recycling, because of course recycling doesn't really solve the problem of too much plastic being in the world, but it also is a problem because you're putting together different types of plastics with unknown chemicals. So the resulting mix is even more specified, which makes getting health data from that really complicated. And we don't actually know if bio-based plastics are better because chemicals are also used in there. So what do these chemicals do? And we should actually regulate, or can we regulate, fiber or chemical shedding from textiles? So I want to leave with some more uplifting messages, because there are things that we can do, right? We can use less plastics in our homes, and we know that ventilating helps. So either ventilate or have an air purifier really lowers your exposure. Studies have also shown that vacuum cleaning helps in lowering your exposure. And with respect to the chemicals, if you don't heat your food in plastic containers or store it in plastic containers, then you will lower your exposure to the leaching chemicals from plastic. So with this, I want to thank you for your attention and give the word back to the chair of this session.
Thank you very much for that very interesting presentation and focusing there, particularly on the end, the leaching from nylon. That was very interesting. The link to chemicals and the fact that you're only studying 2 out of many more. So very interesting. Thank you very much. And leaving us with some of the individual things we could do leads us on actually very nicely to our next presentation, perhaps where we talk about what can be done at the international level for the greater good of us all. So if I pass over to Kay Ono-Woodall from the BRS Secretariat. Kay, please go ahead and introduce yourself, and I will bring up your presentation as you speak.
Thank you very much for the introduction, and thank you very much for the 2 interesting presentations. They are very particularly technical and presents really how microplastics can affect your health in the usual way of using these from air and water. My presentation will focus on what can be done at global governance side or by national regulatory framework. And the title of the presentation that I agreed before INC 5.2, of course, was the updates from the second part of the 5th session of the Intergovernmental Negotiating Committee on Plastic Pollution. Next slide, please. Thank you. So I'm very sure that many of the audience today have watched the news or read the news articles about the very recent meeting that took place in Geneva. And the outcome of that meeting was that there hasn't been any text that was agreed upon by member states. So this negotiation started as a follow-up to UNEA Resolution 514, adopted in 2022. And following this resolution, there was an open-ended working group to start the meeting arrangement. And then the INC has met 6 times as listed here. Next slide, please. Next, please. Thank you. So at the very last session, there were a number of versions of draft text of this treaty, and that includes several provisions that could potentially relevant to addressing microplastics at the international level. The first 2 that relates to upstream, one is on articles about plastic products. If there will be a reference to plastic products that contain intentionally added microplastics, like, for example, those products in cosmetics, or also in, for example, used in agriculture and or even for pharmaceutical purposes as well, there are several products that contain intentionally added microplastics, and such reference could remain in this article on plastic products. Another relevance is on a plastic product design article. If there will be a call for measures to improve plastic product design to minimize releases and leakages of plastics to the environment, including microplastics, this could also be of relevance. Then the third article is about releases and leakages. So for this, you might know that releases and leakages could occur in many different stages. It could be at the very first level when plastic resin pellets are shipped. It could also be released or leaked during the use into the air, like textile shedding, and then during the waste management as well. Connecting to the waste management, the final article that could be of relevance is article on plastic waste management. Although this provision focuses mainly on how the waste should be managed and so on, but it could help avoiding secondary microplastic generation by preventing mismanagement. Next, please. So it was quite challenging meeting, but we could also look at a bit of positive side, focusing on what are currently available in the under the existing mechanism. And this is a very beautiful picture of Hawaiian beach resort. Next, please. When you then focus on the sandy beach and try to look for little shells, and that in this very same beautiful beach in Hawaii, you could see a lot of microplastics beached on the many areas, not just only small portion, but in large quantity, like you can see in this picture. Next, please. And so microplastics could be leached to the environment from so many different sources. From the first picture shows leach from the waste management plants, and then another very important source is from road, like tire abrasion. These such little microplastics particles could be found as a part of street dust, and this could be washed away during heavy rain events and so on. So this could be such microplastics from tire abrasion or part of street dust could contain a lot of hazardous chemicals and could be very concerning for environment and health. And then the leakage from the small plastic resin pellets could happen during the shipments. Also potentially discharging from water treatment plants. And then another large input could come from agriculture or aquaculture. Here I have some pictures of fishing nets and some fishing gears that could be discarded and eventually become microplastics as they get broken down into smaller pieces. So there are so many sources potentially. Next slide, please. But some of the existing multilateral environmental agreements can play a role to reduce such releases into the environment and manage plastic waste so that it could have better addressing plastic pollution, including chemicals in plastics. So here I have my slides summarizing the key elements that the existing multilateral environmental agreements that are Basel, Rotterdam, and Stockholm Conventions could contribute to this very important challenge that's faced at the global level. The first one, the Basel Convention contributes to, is on control of transboundary movement of plastic waste. And then the second important pillar is to minimize the plastic waste generation and manage it in an environmentally sound manner. And then to identify and control chemicals associated with plastics. Next, please. So Basel Convention recently adopted plastic waste amendments, and this have clarified the types of plastic waste that are subject to prior informed consent procedure. Basically, all of the mixed plastic wastes, as well as plastic waste containing hazardous components, are subject to prior informed consent procedure. And only clean and sorted waste can be traded without this restriction. Next, please. So it acts like a traffic light system and avoid having the mismanaged plastic waste be traded to the countries that do not have capacity to manage these waste. Next, please. Yes, so the plastic waste management includes sorting, collection, transportation. Next, please. And the final disposal stage. So it could be done in an environmentally sound manner, or it could be done with a very heavy impact on the environment and health. Next, please. And then another area I mentioned was chemicals in plastics. Also, Barbara mentioned that it could be that microplastics is impacting health or the respiratory system, but the chemical that could be leached from plastics might be the culprit of such symptoms. So it's important to manage chemicals in plastics. And next, please. The Stockholm Convention controls a set of chemicals called persistent organic pollutants and also encourages alternatives to POPs not to have such hazardous characteristics. Next, please. Currently, the convention lists 37 chemicals or groups of chemicals as persistent organic pollutants, and of which 19 of them are plastics related. Many of them are intentionally added and intentionally used for example, purpose of protecting the plastic products from fire or from oil resistance, water resistance, and so on. But some of them are unintentionally released, like dioxins and furans. If they are burnt without control, these hazardous chemicals could be released from these waste management plants. Next, please. Yeah, so the chemicals as a persistent organic pollutants found in products. The products includes variety of industrial uses or everyday use. Most of them are shown here, not single-use plastics, but you can see them in your everyday life. and it could have impact once it is released into the environment as waste, or also during the use if it is part of textiles like carpets or furniture. Next, please. The Stockholm Convention has the mechanism to add new chemicals, and that is why, although it started with 12 chemicals, currently it has 37 chemicals. And one of the most important criteria for POPs is the long-range environmental transport. Next, please. It is because that the fact that the chemical impact is not just only limited to the country of origin, it requires global action to control such chemical production and use. So the long-range environmental transport for one of the chemicals recently listed called UV328, this was studied from seabirds. Next, please. So this one is the seabirds called blue petrels. They live in this southern hemisphere, Atlantic Ocean and surrounding ocean. As you can see, the bottom one is Antarctic, and these dots are where they were found. Next, please. In this found in the seabirds, the seabirds produce green gland oil, and you could find this plastic additive called UV328, and that was found to be one of the proof for having long-range environmental transport. So the plastic additives could travel through ocean currents, of course, but also not just only that, but also through migratory species. And that can be also have impact, not only that species itself, but can have impact on the areas that are far from the generation or use of that chemical. Next, please. So in the POPs Review Committee's concluding statement was that UV328 is likely, as a result of its long-range environmental transport, to lead to significant adverse human health and/or environmental effects such that global action is warranted. So now this chemical, UV328 and plastic additive, is listed under the Stockholm Convention in Annex A, which is for elimination. Next, please. Another chemical I wanted to mention is the PFAS. So Stockholm Convention lists 4 groups of PFAS currently: PFOS, PFOA, PFHXS, and long-chain PFCAs. So you might know that PTFE, polytetrafluoroethylene, PTFE is historically produced from non-polymeric PFAS like PFOA, and this polymer, PTFE itself, is very stable. It's very stable, and that is why used in plastics, and it doesn't react with anything. However, after the use of PTFE, of course, it could break down into smaller pieces. It could contribute to the environment as microplastic particles. And if PTFE contains some residual PFAS or additives, then it might have impact on environmental and health. One of the concerning uses when this PTFE is turned into micropowders, so it's like a very small particles, and such PTFE micropowders are used in lubricants or sprays and coatings, and this could lead to direct environmental releases, and therefore it requires a bit more of attention. Industry is making efforts in managing such potential risk, so it has some guidance on how to use in a safe manner, and also on information sharing as well. So that was my last slide. Thank you very much for the opportunity to share perspective from BRS conventions.
Wonderful. Thank you very much, Kay. That's very useful and valuable for us to hear hear those links. Okay, great. Well, we have about 20 minutes for questions and answers. So we have our three panelists. So I invite those who are participating to put their hand up, and we'll invite you to ask a question, or put one in the chat and I will help read it out. So over to participants, please to ask any questions that you would like to follow up with our participant or our panelists on. I see we have our first hand from Catherine Santiso. Please go ahead, Catherine, you have the floor.
Yes, hi, good afternoon, good morning, good evening, wherever you all are. Thank you for the presentation. I had maybe two quick questions on the presentations, the earlier presentations. So my first question would be, I guess, to Thomas, if I remember the name right, on the Switzerland model. It seems like a lot of work has been coming out of Switzerland. So I guess one question for those outside of Switzerland would be, what learnings or what can be utilized from the work that's being there outside of Switzerland? And then maybe as a follow-up question for both Thomas and Barbro would be, what links maybe can be seen between the exposure considerations in Switzerland and the human health that is being mostly worked on as a Netherlands cohort?
Okay, thank you. Thomas, I'll open up to you and then we'll let Barbro afterwards provide some thoughts. So Thomas, over to you.
Yeah, thanks, Catherine. These are not easy questions, I would say. Switzerland is probably comparable to many other countries in Western Europe, at least, or that have a similar lifestyle. Let's say that have similar products on the market. It's also the case that Switzerland adapts more and more European law. So we since we are a small country really in Europe only, it doesn't make sense that we do everything alone. So we increasingly team and join forces with the EU. In that respect, I guess there is some similarity regarding lifestyle and consumer product uses and so on. It would be courageous to make any more specific statements, I guess, for the rest of the planet. What we tried for decades as a society, as a Swiss society, is really to push environmental law enforcements and be rigorous, and probably Georg Karlaganis is much better competent to answer along these lines. So Switzerland has been pioneering some environmental kind of cleanup, some avoidance of emissions, some becoming a green economy if you want. But yes, that's all very general. I'm aware of that. And the other question is probably even more difficult in terms of exposure and human health. If I may, I leave that one to Barbro. I'm sure whether she likes that, but maybe you can help me a bit there, at least.
Thank you. Not sure if I should thank you for this, but yeah, so I think the studies like Switzerland are really important because we need very granular data about how much is in the air in the different places. But if I may advocate for one glaring knowledge gap, is the fact that we don't have any studies where air concentrations are measured at the same time as internal concentrations. So, and that is something we really need to be able to estimate human exposure, is how much is in the air, how much gets into the lungs, how much gets out again, how much is exhaled again, because the really small particles might be exhaled again. So we really need studies that really look at that, both indoor and outdoor, I would say. But of course, it starts with getting as much data from the air as possible. So that's why the Swiss measurements, I think, are really nice.
Okay, thank you very much to both of you for giving that a go. I don't see any more hands at the moment, so I'll give people a little bit more time or send it in the chat. Thomas, I noticed we asked if we could share your presentation. You said, unfortunately, not at this point because you have preliminary results. Do you have an indication of when they will be confirmed or verified and that kind of information could be shared? So just be interested in that.
Yes, sure.
Thanks.
Sure. Sorry for that. I had to decide whether I show you the old stuff that is published and boring, or whether I try to be upfront and provide you a glimpse or a flavor of the brand new data that comes out from our laboratories. These are, as I mentioned, this is the work of three different PhD students, and they all will conclude their theses by the end of next year, I would say. And by then, those respective publications will hopefully be published and can then be, of course, shared as well.
Okay. Wonderful, thank you. No, I think we all very much appreciate access to this, even if preliminary, and we'll be keeping an eye out then for that publication. We do have one hand up. We have Biagi G. I imagine there's a different name there, but please go ahead and ask your question. Thanks.
Hello, everybody. Good morning. Thank you for all your very nice presentations, very interesting. My question is for Barbara. I would like to ask you if you could clarify how shapes of micro nanoplastic shapes can affect the toxicity inside the lungs and the intestines. Thank you.
So actually, for microplastics or micro nanoplastics, we don't have that data yet, but we know, for instance, that asbestos fibers are really toxic, and that's because of the material they're made of and the shape they have. And of course, there are microplastic fibers, and one of the issues with the asbestos fibers is that they're very rigid, and that also happens with microplastics. So you could see some analogies there, but that there's no data to support that, right? It's an hypothesis, and it's very. So what we actually need is somebody comparing the same material, different shapes, and different assays to be able to say a little bit more about what makes toxicity for microplastics. Is it what shape is more toxic? What surface coating or surface area, what the surface looks like. And there is just not enough data to be able to give you a clear answer here, unfortunately. But we do know it matters for other types of particles.
Thank you so much.
Thank you. Over to, we have Helene Walsh. Please go ahead.
Yes, thank you very much for the interesting talks. I would have a question to Thomas and to Barbara. The first one is about the air measurements you did in Switzerland, and you showed some data which were actually below the LOD. So I'm now wondering, how can you show data below LOD? How do you determine an LOD? And yeah, what's the reason for that?
Yes, an important question, and particularly for clean environments such as Swiss air, it seems, in many respects. So the limits of detection is either determined by the precision of replicate analysis at low concentrations, because that defines uncertainty, and uncertainty will somehow then give you a lower range of the quantifiable the domain of your analytical method, or it is the blank level. That means that the number or mass concentration that you quantify in any kind of procedural blank, ideally a field blank or at least a procedural blank in the laboratory. And you're right, that can spoil your whole analytical chain. And it is correct for more remote locations, such as the one in rural Switzerland, but often also in remote areas, Arctic and other situations. The blank level will determine more than the precision what is actually quantifiable in a reliable way. And this is one reason why I showed only, or I declared that data as preliminary. We have been working on reducing those blanks and throughout the analytical chain for quite a while, for years almost. We are getting better and better, but still it's never zero. So you somehow have to account for those uncertainties and for those levels that you see and everything. And there is an internal discussion, is it that we have in the group as we speak? Should we subtract the blank from what we quantify or not? Is there a causal relationship between a blank level and any given real sample? We haven't come to a overarching consensus even within our consortium, honestly. But what we agreed on is that we should report openly and transparently how we do things and how we calculate things and what assumptions we take at any step. And we have to be transparent with the fact that, yes, we fight against those blanks. And at some point, we have to take that into account and discuss our results accordingly.
Thank you very much. That clarifies it a lot. Thanks. And another question to Barbara, if I may still.
Yep, go ahead.
You talked about indoor and outdoor environments and concentrations in the air, and that in general the indoor environment is more polluted, which makes complete sense to me. But I was wondering, do you also have information about hotspots in outdoor environments? So is it really better in every case to open the windows, or what if you are living next to a high traffic road, for example, or other pollutant sources?
Very good question. Yes, I didn't address those little tweaks because, of course, if you're living in Beijing or Mexico City, where the pollution outside is really high, then opening a window might not be advisable. So if you're living in a really polluted city, I would go for an air purifier. But also, for instance, in the Netherlands, or the north of the Netherlands, I should say, which is relatively clean. If you live next to a busy road, of course, the outdoor will be more polluted than in a more rural area. So in that case, I would ventilate at night when there's less traffic. So I would sort of adapt the advice based on what is generally found. But generally, at least in the Netherlands, the indoor environment is much more polluted than the outdoor environment.
Okay, great. Thank you.
Great, thank you very much. Thomas, we have two questions in the chat. Have you seen those, or would you like me to read those out?
Yes, I've seen that. I don't know whether I got them correctly, but one question was related to, let's say, fragmentation versus bio or degradation, if I'm not mistaken.
Yeah, yeah.
And yes, that is often a matter of confusion because particularly in the past, there were many polymers out there or products that are what they are called oxo-degradable. That is, they would rather fragment into smaller pieces based on some specific bonds in the polymers, but they wouldn't really be oxidized to carbon dioxide. So I think it's important to make the difference between plastic fragmentation, and some of the speakers today have also alluded on that often you have to start off from macroplastic, and then by physical shear stress and so on, the particles get smaller and smaller, but in terms of actual polymer mass, they are still out there. So it is essential to differentiate between simply the fragmentation where the polymers are still remaining, but actually the number concentrations of particles are exponentially increasing, and true degradation that is actually oxidation of your carbohydrates to carbon dioxide in the end. And I think the beauty in the study that we did together with Michael Sander and his analytical method was really that we were quantifying the polymeric rests and could do a mass balance really on the basis of the polymer itself. And it's actually exactly what you see. The mulching foils, for instance, they would decompose, and with the naked eye, you wouldn't see them anymore. But if you do an NMR-based analysis after extraction of the soil, you would still see those polymer chains as kind of shifts in the NMR spectra, for instance. So they haven't really fully decomposed or biodegraded, but they have been fragmented into really oligomers. So it is an important point, and it's often not properly addressed or understood by the communities and the stakeholders. That was the one question I saw. I didn't see the second.
Yeah, thank you. And then it said there was one regarding the soil type 1, referred to as an acid soil in Thomas's presentations. Can you give a little more information on what type of soil this was? Was this a peat or organic type soil? And then there's one more, and then I will close it there and move to our concluding remarks.
Right. I think it was, I gave the soil type. It was a loamy soil, actually, as opposed to a silty clay or a clayey loam in other situations. We were astonished ourselves that this being so close together, that the soils would show such large differences, and we are not aware of any kind of physical manipulations of those sites. So the differences are considerable. It is known that acidic pH have a drastic effect on soil microbiomes in general. So that must be a completely different community. And also in terms of, let's say, what's that called? Abiotic hydrolysis of some of those biodegradable mulching foils, the difference is certainly also considerable.
Okay, thank you. And then we have a last one about modeling versus field measurements. Are you saying the modeling results and the field observations were in agreement? Is this case specific, or does it reflect results across wastewater, agricultural, and aquatic environments when predicting microplastics?
Well, I can only respond to the specific situations that we have tried to quantify and to get actually analytical measured data from, and that is that project on atmospheric deposition, and that is those analysis that we are currently doing in wastewater treatment plants, specifically sewage sludge, activated sludge. And there, I would say we were positively surprised to see that modeled and analytically measured numbers are in the same order of magnitude. I think particularly for modelers, they are very happy if their models are within one order of magnitude of real measured data. That's a success, and vice versa. I simply wanted again make the point that this is really work in progress as a research community, and we really have to team up and do those complementary that is complementary work. Bernd Nowak is one of the leading modelers, mass flow modelers on that planet. That's the best we can do by modeling. I'm sure about that. But of course, it needs cross-validation with actually measured data. And often, Bernd is so successful, to put it that way, with his research, simply because analytical chemistry lags behind and cannot cope with the complexity of actual environmental trace analysis of those, needle in the haystack kind of analytes. So it usually takes a decade or two, and that is true for all pollutants on that planet. It takes a decade for the analytical chemist to develop tools that can quantify any kind of pollutants in the concentration range that is necessary, that is usually in the trace at the trace level. So and that's the good news. The analytical chemists are making progress. We are making progress in our endeavor to be able to quantify these components. And that again helps to validate the models, to improve the models. The models again will teach us and where to look for things and about what concentration range to be covered. So it really needs both ends in a complementary way. That's my opinion about that.
Okay, thank you very much for adding in there. That's great. Okay, we will move to concluding remarks. So my colleague George Karliganis, who's been working in this area for a long time. George, I'll pass over to you just to close us out, please. George.
Thank you very much, Oliver. Dear participants, my name is Georg Karliganis from UNITAR. First of all, we would like to thank all participants for your participation in the webinar, and of course, our special thanks to our speakers, Thomas Bucheli, Dr. Thomas Bucheli, Professor Barbara Melgert, and Dr. Kei Ono Woodall for their great commitment and insightful presentations. They have invested a lot of time and energy in this event. We received from Thomas Bucheli from Agroscope in Zurich an insight about the use of plastic in agriculture. It is widely used because of its advantages, such as overall higher crop yield due to the extension of the cultivation period, crop protection, prevention of soil erosion, and other advantages. Plastic mass flow analysis of individual applications showed that polyethylene PE mulching foils can be locally relevant. Alien plastic material in compost and digestate can be also locally relevant. Predicted environmental concentration, PEC, was 0.02% or 200 milligram per kilogram soil based on worst case assumptions, with the sources littering, sewage sludge application until historical application until the year 2005, compost and digestate applications, and PE mulching foil applications. Those response studies of effects of plastic on terrestrial organisms resulted in a predicted no effect concentration PNEC of 0.05%. Preliminary risk assessment showed a risk quotient PNEC of 0.4, which is no risk. However, this result is based on several incertitudes. Non-degradable polyethylene is increasingly replaced with biodegradable mulching foils made of PBAT and polylactic acid PLA. Incubation experiments with 3 different soils were made in the laboratory, in greenhouse and in the field with PBAT and PLA compared to polyethylene and polyhydroxybutyrate hexanoate PHPH. Atmospheric microplastic decomposition was monitored at 5 locations over a period of 1 year, and microplastic occurrence was quantified in activated sludge of 51 wastewater treatment plants all over Switzerland. Preliminary results show annual countrywide mass flows in the order of a few hundred to a few thousand tons for atmospheric deposition and emission to surface waters, respectively, which are comparable with model predictions. Note that since 2005, sewage sludge is no more used in Switzerland on the field. It is burned in incinerators, including the microplastic in it. And at this point, I would like to tell you a small anecdote on sewage sludge incineration in Switzerland. The reason it was sewage sludge was banned 20 years ago by the Swiss government. And the reason was not microplastic, and also it was not PFAS. It was the fear of Switzerland of prions from mad cow disease. So Switzerland was afraid of mad cows at this time. And this was the reason. This gave the political push really to push this through, and from that cantons started to build incinerators to incinerate the sewage sludge. Now to the second presentation, we learned from Barbara Melgert from the University of Groningen that the exposure to microplastic in the air outdoor is lower than indoor. Outdoor is mainly from the tire abrasion. Indoor exposure is mainly from textiles like polyester and polyamide nylon. These microplastics are also found in lung tissues. The microplastic toxicity depends on dose, size, shape, surface, and associated chemicals. The number of chemicals found in plastic is over 16,000. A few of them, the POPs, persistent organic pollutants, are regulated globally in the Stockholm Convention. There was the research question. Barbara Melgert asked herself, what do textile microplastic to the lungs? Epithelial cells and immune cells are first exposed to microplastic in the airways and air sacs of the lungs. Immune cells chase and eat nylon fibers and become inflammatory. Exposure to nylon and polyester results in fewer mini airways. Nylon leachate inhibits airway growth. Many questions remain to be open. What can we do today in our daily life? We can use less plastic. We can ventilate the indoor air. We can use air purifiers, and vacuum cleaning can help also. Due to leaching chemicals, we should not eat and microwave from our food from plastic containers. Now to the third presentation. Ki Ono Woodall gave us a very comprehensive update about the Plastic Conference INC 5.2 in Geneva. Provisions relevant to microplastic in the draft text of this conference are the articles, the article on plastic products, the article on plastic product design, the article on release and leakages, and the article on plastic waste management. Sources of microplastic in the marine environment are air-based, land-based, or marine-based. Key elements under the BRS conventions are control of transboundary movement of plastic waste, minimization and environmentally sound management of plastic waste, and the identification and control of chemicals associated with plastic. Basel Conventional plastic waste amendments are the Annex 2 plastic waste including mixtures with the symbol Y48. Then it's the Annex 8, Roman 8, hazardous plastic waste with the symbol A3210. And at the Annex Roman 9, clean plastic waste for recycling with the symbol B3011. There are 37 POPs and 19 plastic-related chemicals in plastics under the Stockholm Convention. Long-range transport is important to classify a chemical within the scope of the Stockholm Convention. Long-range transport can be monitored in seabirds. Chemical additives in plastics, such as UV 328 and legacy POPs, can be transported via plastic debris in long-range oceanic transport. PTFE, polytetrafluoroethylene, is a source of microplastic and also a source of PFAS exposure. Once again, many thanks to our speakers and thank you for your attention. And over now to Oliver.
Thank you very much, George. And with that, we'll close up. Thank you very much to our speakers, particularly Thomas, Barbara, and Kay, for joining us. It's a great pleasure. We will share as much information as we can with participants. I know, Thomas, in particular, you've given us some articles that we could share, so we'll look to do that. Thanks to my colleagues in UNITAR for helping to set this up, Manoush in the BRS Secretariat, who equally helped in setting up the webinar today. And we do hope to continue our webinar series. So colleagues who are on this webinar today, please do get in touch with us. If there are any topics you'd like us to dive deeper into, any alternative topics within the nanomaterials area, we would gladly look into it and see if we can share more of that information with you. So in the meantime, please do keep an eye on our websites, both UNITAR and the BRS. We will ensure we share information on any upcoming webinars or information we have, and we look forward to communicating with you all in the future. So thank you once again all, and we'll close there. Thank you. Have a nice day.